Good morning. Today we are going to talk about microarchitectural attacks. Before I begin, I wanted to know how many of you have taken any course on computer organization or computer architecture? Not everyone. How about compiler? How about
compiler yesterday?
they should raise their hand. How about operating system? Okay. So what I will do, I will spend 2 to 3 minutes on each subject. I will cover a subject in 3 minutes, and then those features we will talk about how they can be used for microarchitectural attacks. So basically, I am going to talk about some of the famous attack, and then I will talk about what is going on as we speak today, what are the things. And even before I begin, I want to tell you, any microarchitectural feature that you know, pretty much somebody already came up with an attack. Even microarchitectural feature that does not sound like a architectural feature, like dynamic power management, which I am not going to talk today. Even dynamic power management, somebody figured out during that slowdown process, architecture goes through certain states that can be exploited. So if you do little bit of study and figure out a microarchitectural feature for which there is no common vulnerability in the database, that would be your paper. Or somebody came up with a new architectural feature to improve performance improvement, and of course, nobody came up with an attack yet, that would be your attack vector, and I want to walk through. So, I am going to talk about 3 microarchitectural feature: out of order execution, speculative execution, and different microarchitectural structures, like think of buffer. And these, if you took architecture, you know these are the ones that used to improve performance. So, before I go, so a very quick beginning of computer organization course. If you look at architecture, it can be kind of looked in an abstraction way. Application software, all of you know, the programs you write, that is the application software. Below system software, some of you may or may not work depending on if you are working in operating system, compiler, linker, loader, all of those most people do not play with them unless they are researcher or they are the developer for that. That is a small fraction of people. Even smaller fraction of people actually work on the architecture space. So, people like Professor Korfa. So, then even the architecture can be viewed in 2 parts: instruction set architecture, think of addition, subtraction, multiplication, and then the implementation, think of pipelining, branch predictor and all that. Can anybody tell me? This is clearly understandable. The people who are writing program does not have to deal with linker, loader, compiler, understandable. Why do we have a layer instruction set and implementation? Whom does it help, this abstraction? A compiler writer, which is in this layer, does not need to know all the details of this architectural specific that we will talk today, and then we will talk about the attack. They do not need to know all these details. All they need to know, what instruction do you support, add, subtract, multiply, what registers do you provide, so that I can generate compiler code. What is the minimum I need to know about the computer architecture, so that I can produce the binary or assembly. So, compiler writers or even operating system people or anybody in this layer does not need to know everything or every tiny bit of detail, that is the abstraction. But the people who are actually designing the microprocessor, writing the Verilog VHDL code or writing the simulator for that architecture, whether it is ARM, whether it is Intel, whether it is AMD, they need to know this, very small fraction of people. So, if you want to put percentage, this is probably 95% of the people, this is 3 to 4% of the people, and this is probably 1% of the community. Any questions on this abstraction and who it is used for? Now, this is one slide course on compiler, okay, that I need for my architectural attack. For compiler, the job is you give a high level language, it could be C, Java, Python, whatever it is, and the standard definition of compiler is you take something in high level, transform into slightly lower level details. In this particular case, this is the high level C program, this is basically a ARM assembly code, and then there is something called assembler, which produces the binary, 32-bit binary or 16-bit binary. In ARM supports 2 types of binary, and that binary will run only on ARM processor. This assembly will also run only on ARM processor. This program can be compiled on any processor. Now, for normal people like you and me, compiler and assembler are together called compiler. You take a high level description, you generate the binary. For microarchitectural attack, mostly we are interested in two instruction, if statement and load instruction. So, this load if is not here, but if would be a branch kind of instruction. Those are the two instruction. If you write a, let me annotate it here. So, those are the two instruction. As far as compiler knowledge is concerned, all I care about, if there is an if here, compiler will convert into some form of branch greater than equal to or something, that instruction we are interested in, and whenever there is a access to any variable or an array, that would be converted to a load instruction. So, if you can figure that out, that any access to an array element or a variable, everything would be stored into the memory. So, to bring it to the register, you need a load instruction, that is the load we are interested in, and any if statement or any for loop in your program would be converted to a load instruction, and any array location on the left hand side, that would be store instruction. Any question on this basic idea? So, we are done with compiler for today. Now, we have 2-3 slides for the architecture, specifically the architectural features that I am going to attack. So, when you look at a computer architecture, you have your CPU or a processor, which will have a register, then you have a cache, then you have a memory, then you have IO devices. You can think of this is a hard disk, this is a flash drive, whatever it is, right. Now, anybody knows what is the utility of memory? Probably understandable, and when you buy RAM or RAM stick or any extra thing, that is really the main memory. And this is your flash drive. Think of a USB stick, in early days there we used to call it hard disk, which is not popular anymore, but whatever it is, that is basically that one. Anybody knows what is this cache used for? Since some of you have taken the course, yes please.
So, parts of the program which are most likely to be executed by the CPU are cached into the cache from the memory.
So, cache is a smaller area that you keep closer to yourself, so that access time is faster. So, roughly speaking, if this is a 1 gigahertz processor, typically 1 nanosecond access time means 1 cycle access. So, technically speaking, this is also a cache, so we do not call it. So, this is roughly less than a nanosecond, you can think of this is about 0.25 nanosecond typical access time. So, you can think of this is first level, something smaller you keep closer, so that you can access it faster. Ideally, I would have liked to keep this one closer to me into the integrated circuit, but you remember integrated circuit or the SOC is few millimeter square, right, few millimeter square. So, then within that space you cannot accommodate hard disk, and typical size of this disk or the amount of memory you can see it is 10 gigabyte in the 2 to the power scale, somewhere around 2 to the power 40 to 2 to the power 50, that is kind of the space, and that you cannot accommodate within a tiny area. So, that is why you have to keep it far, and further you keep, then it will have a longer access time. How much longer? So, main memory is typically 100 cycle in this example, because 100 nanosecond, and this is about 5 million cycle, millions of cycle. So, this point is important for my attack, that if something is in the cache, so initially is nothing in the cache, the program is also in the hard disk that you loaded, the stored, and even your data is also in the, if you have any initialization data, your everything is here. First instruction you access fetch unit, it goes here, it is a miss, then it goes here, it is a miss, then it goes here and it gets that data, and then that's return story happens. Only difference is here you bring something like a block, think of one variable, here you bring, we call it something like a page, think of a truckload of data, you are going far away, you are bringing a truckload of data and you are keeping a small portion of it here. So, the size of this one is typically called block, you can think of just one variable, it could be few variable, this is a page, could be 1024 variable, about thousands of variable here. So, that is basically the story. Any question on this? So, only thing we need from this diagram if processor requests a load instruction and data is in the cache, it is going to be very quick. But if processor sends a request and the data is not there, it is going to take time, whether it is going to take 100 cycles or million cycles, that is different, but it is not one. So, there is this timing difference. This timing difference we are going to use for the attack. Anybody has any question on this, the distance delay trade off? If we had a choice, we would have kept the whole hard disk inside the CPU with one cycle access, but that is physically not possible. Okay. Now, little bit of introduction to cache. So, this level of detail is not needed, I kind of talked, but what is needed is when you go to a cache or memory, when a load instruction comes in, it says load to register R1 from some address, let us say location 543, that is not a valid location. Can anybody tell me why? It has to be a 2 to the power number, but either way, let us just say there is a location called 543 and which has some value, let us say it is a love sign. So, the objective of this load instruction is to get the data from that location, 32 bit data, 64 bit data depending on, and put it into the register. But it is just that before it goes to the register, it goes to the cache, and when it goes to the cache, there is a mechanism. This is a simple direct cache, and the value which is basically this value, it would come there, and cache being small, let us say cache has only, this example cache has only 8 locations. So, the implicit address is 3 bits, 2 to the power 3 is 8, but the remaining 32 minus this 3, of course, minus the word size, that need to be stored as a tag. So, there are all these intricate details and each of them are used to mount the attack. There is a valid array to say it is actually valid, there is also a dirty array to just say it is dirty. Anybody knows why that dirty array is used? The name is does not sound nice. Why that dirty array is used?
If it is not updated, then it is dirty.
Yeah, so basically most of the time processor writes to the cache, they do not want to write it back all the way to the main memory, it takes a lot of time. You write to the cache, and the idea is because of this locality we might use it again. So, we do not want to write it back unless when it is absolutely needed. It is absolutely needed when there is a context switch, one program gets interrupted, another program starts executing, or when that program completes. At that point, you had a choice of writing all of these locations to the main memory and hard disk, or just look for the locations where 1 is marked, those locations have been updated. The locations that has been only read and never modified, you do not have to write it back. So, there are all these features and each of these features is used for an attack. I am going to just show one of them. Any question on this cache design? Caching, you get the data, keep it near you, so that you can access it again and again and again. Like the in a for loop, if you have instruction, same instructions are getting accessed again and again and again, because that for loop is executing. Same thing about data. Data also has the same level of temporal locality and spatial locality. Temporal locality is if I access the data right now, I am going to access in the near future. Spatial locality is if I accessed an array location, this particular array location, there is a high likelihood I am going to go to the next location of the array, right. So, that is about the cache. Now, out of order execution, this is exploited by meltdown. So, let me explain what is out of order execution. Out of order, so what is in order execution? If this is the program, this is the first instruction, this is the order, processor should execute this one first, then it should execute this one, then it should execute this one. That is basically in order execution. But if you look at here, first of all division takes a many cycle depending on which processor, anywhere between 15 to 30 clock cycles, 30 nanosecond, think of it. So, division takes that long, and division is producing this register 3 which is consumed by this one. So, the add instruction cannot start until division finishes. So, that means this one has to wait for, if it started, let us say it takes 24 clock cycle, it needs to wait 23 clock cycle. But if you look at the subtract instruction, it has no dependency, no data dependency, and there is no if, branch, for, nothing in between them, no control dependency. Now, sometimes it may not be visible to you, but there may be a so entry point of another branch from somewhere, that is also a dependency. So, there is a if statement or branch greater than that jumps to this location. So, then this is still a control dependency, but let us assume none of those exist. Nobody jumps inside, nobody jumps outside, no control dependency, no data dependency. In today's modern processor, what will happen? This instruction will be executed before this one. Division is executing, subtract will start executing, assuming you have more than one ALU or the ALU adder subtractor is available. So, that structural, no structural hazard, no data hazard, no control hazard, it starts executing early. This is out of order execution. So, fetching of instruction is in order, execution is out of order, but towards the end processor makes certain choices. So, this is let us say it is a fetch, then you have decode, then you have execute, then you have memory and all these stages, then you have write back. So, fetch is in order, this decode execute, this is out of order, like the way I moved the instruction, and again here many processor enforce in order, some statically controlled do out of order, but that is in order, because if somebody you executed out of order and then you are not supposed to finish it or write it, if you write it then you say oh I made a mistake, then you will not be able to do anything, right. So, anybody has a question on out of order execution? If some instruction is ready to execute, all the operands are available, no dependency, processor executes it early, right. This executing early is the attack I am going to talk about. One more architectural features I want to bring, virtual memory, right. So, in the virtual memory, the key idea is, it got introduced in 1960s by IBM, but the key idea is, when there are many reasons. One reason is of course for security, another reason is when compiler compiles a code, it does not have to worry about which exact memory locations I should use. So, then when compiler this process 1 is executing instance of a program, think of this is your program 1, this is your other program. Now, this virtual memory gives you the feeling that compiler or the program has all the memory to its disposal. How much is it? If you have a computer with address bus size 64, then it is address 0 to 2 to the power 64 minus 1. This is address 0, this is this location is this location 2 to the power 64 minus 1. Now, this has two problems. This virtualization is easy for the compiler. Compiler does not need to know where should I start with the first variable. Most of the time compiler starts with first variable in location 0. Now, before I talk about this, you have to understand physical memory size is 0 to, depending on processor it is different, but there is no physical memory I know of today that is 2 to the power 64. So, most computers have something in the vicinity of 2 to the power 50. 2 to the power 50 minus 1, 2 to the power 52, 54 in that vicinity, right. So, you can see there is a fallacy here. This program thinks I have location 0 to 2 to the power 64 minus 1, everybody thinks exactly the same. Operating system being a program, operating system also thinks I have that. If you add it up, all of these locations, clearly it is larger than that number. Luckily, nobody writes a program or the data does not take that much of space, luckily. That is why all of this space together fits there. No matter what it is, this whole virtual memory or the operating system that I did not introduce the course, it does few things at this point. What it does, this physical memory, it divides into multiple parts. Operating system being the boss, it keeps some privileged area for itself. Let us just for the sake of argument assume 0 to location 9 it keeps for itself. Of course, it keeps much more than that, right. This we call kernel space or operating system space, and all attacks are all about, can I access the kernel space, can I behave like a super user. If I can access super user, then I can do lot of stuff. So, this is the kernel space, and there are many other spaces. Let us just for the simplicity assume there is a kernel space and there is a user space, right. Once you have user space, now in a server environment there could be multiple user. Even if you think I have my own computer, you might have a guest login, you might have a the login that you have privilege to install stuff, the login where you do not have privilege. So, let us just say there are two users running here, user 1 and let me do this in a bigger screen. So, this is your physical memory, and physical memory I am dividing into two parts. This is kernel part or operating system part, super user part, whichever you know. This is the user space, and the user space there could be multiple users. Just for simplicity, let us assume there are two users. So, this part is for user 1. These are exact addresses. I am not writing it. If you want me to write, this is 0 to 9, let us say this is 10 to 19, and so on and so forth, total space. Forget about user 2, let us not talk about user 2, because we are interested. This is you and this is me, let us not talk about me. So, user 1, you might be running multiple programs, your mail tool, your gaming application, your browser. For the simplicity, let us assume it divided in two parts. This is your first program, this is your program 1 or process 1, and this is your program 2 or process 2. Let us just say this is your mail running and this is your browser running, right. So, two of them, each of them is further divided into program part and data part. Operating system's job among all the things is to maintain nobody finds things in other people territories. Even if you are user 1, that is you, this is you and this is me, even if it is your program, between two programs, when this program 1 is running, it should not be accessing any location here when it is doing load store. Even the same program, the program memory, so let us say this is a for or something sitting there or corresponding binary sitting there, that for or any load should not be, that code should not be accessing here, and this data should. How does that happen? Let us say you are doing a Fibonacci series computation and your stack and heap growing, when it keeps growing and growing, it should not cross that line. You are writing to stack and you are calling this recursion, calling and that stack growing and cross that line, operating system will give you a segmentation fault code dumped. When you are doing a load instruction is supposed to access whatever operating system allocated you for this. Now, normally you and I do not pay attention when you run program, how much is it, you can always go in the settings and set how much you can do, but no, whatever you do, if you cross that line, theoretically you can run millions of processes, but if you keep forking lot of processes, operating system will say exceeded, process quota exceeded. Let us say you are doing a fork in an infinite loop, it will say, so the number of process it can allow, number of user it can allow, there is always a limit to it, because this is a physical limit. So, all the attacks I am going to talk about is how a program, of course, this program accesses its own data space, that is legitimate, but this program, any load instruction from here should not be accessing anything here. I mean, that is still not treated as a serious problem, your program versus your program. What is treated as a serious problem is this one, or a legitimate attack is this one. In fact, this is still treated as a not so serious attack because it is still in the user space. What is treated as a serious attack is this one, if you can access anything from the kernel space. And what I am going to show, how to access kernel space, how to access this, and the ideas are very simple, trivial. Is this idea clear? That operating system maintains these lines so that nobody crosses the line. Whenever you do a load instruction, operating system does a trap and checks. So, let us say there is a load instruction and you are trying to load to register R1 from something like 0, this is the address and this is, let us say, R3. So, value of R3 plus 0, let us say this particular value becomes to be 48. It checks, is 48 in your data range? If it is not, so basically it checks, is 48 greater than the lower bound for your thing and less than equal to the upper bound of your data memory. For that program, what data memory? For that user, that program, it checks that. If it is outside, it is segmentation fault and code dumped. Can anybody tell me segmentation fault code dumped, is it a bad thing or a good thing? How is it good thing?
Because it's not allowing for something unauthorized to happen.
Right, but you born now, if you born 20-30 years ago, your home directory space is so little, if there is a core dumped, it creates a file called core, you pretty much can't do anything, disk quota exceeded. So, one error will cause another error, right. So, I did not know what the hell is going on. What I did, I always used to have a create file name core, and then I do minus write permission on core. So, segmentation code dump will happen, but it will not dump. Later I realized that is a stupidity, because this code dump, the core file is actually operating system took a camera and took the picture of all this snapshot from which program, from which line. If this program was compiled with -g, and if you just do gdb core, then it will show you take the pointer exactly to the function which caused the code dump, which function called that function, complete trace of it will give you. So, the code dump is supposed to help you to debug where there is a mistake happening. Of course, in those days assumption was nobody is malicious, but now if this idea is clear, anybody has a question on this, because later I will say, oh, it is accessing somebody's space, you will be thinking, so what? But this is not legitimate. You should not be poking around other people's house, other people's property, other people's privacy. So, this is basically security boundary. Okay. Now, coming back to virtual machine. So, virtual machine is a slightly more complicated idea on top of it. In addition to dealing with this, we also have to deal with the idea that everybody thinks the location 0 belongs to them. So, then there has to be a mapping. So, this also during loading time, what operating system takes care in this main memory, whose program would be loaded where. So, then basically when it loads, so that is your starting address, that is your end address. So, then if first time you are loading or running, maybe your address 0 got mapped to some location, I am just making it up 153, but second time you load, that location might be something else, because that location might be occupied by somebody else. So, there are a lot of this complexity, but this virtual memory gives another dimension for attack. Now that we are, so basically this process is trying to access something here, and that should not be allowed. That is basically in a normal circumstances. Now, all of this is fine, somebody trying to attack somebody, operating system will not allow, processor will not allow, but it leaves a footprint, and footprint it can leave in different way. In this class I am primarily going to focus on cache timing, that is why I spend time, but there are attacks which I am not going to talk, that relies on instruction timing, ALU contention, memory contention, and many of them. So, what is this footprint? Before even I go further, so when you have a processor, then you have a cache, sometimes I write it this way just for fun. When you have a cache, and let us say main memory, ignore about the final level, then when you access a load instruction out of order, that you should not have accessed, and later computer realizes, oh, I should not have fetched that data. So, let us say you had an instruction load R1, and let us say from some location 48, and later it was part of a somewhere it got out of order or whatever, it got executed, processor realizes, oh, I should not have done that, it will not write to R1 that value, whatever value coming from address 48, it will not write. So, that is good part. But where is the covert channel? That data actually came to the cache. It is just that the time it took to realize, by that time data already came to the cache. Remember, cache is sitting somewhere, cache has its own controller, processor does not control the cache controller. Once you send the request, data started coming, data already came to the cache, and cache being in the order of megabytes, and these days actually cache is gigabyte. The idea that every mistake you go and clean all these billions of locations is simply not possible. That is going to be huge performance overhead, nobody implements it. If cache would have been cleaned after every context switch, after every mistake in load, after every mistake in branch, all these attacks I am going to talk about will not happen, at least not through cache timing attack, because you brought somebody that you are not supposed to bring, it is somebody else's data, it just so happened. So, what is attacker doing? Attacker knows 48 is not my location, but it is simply in the attacker program it creates an address, choose an address 1009357, some address you know it belongs to Dr. Korfa, it belongs to operating system, you just issue that load instruction, put it somewhere, make sure processor will execute it out of order or branch prediction will take care of it. I will zoom in to show you how I can make that happen. Then I get that data into the cache. Now, how do I get it from the cache? I will talk in a minute, but I just simply want to say you can bring anybody's data into the cache, you as a attacker program. So, in the security community we differentiate, one we call attacker program, the next one we call victim program. Victim program is whose data you are trying to get. Any questions on this idea? Yes, please.
This will be limited to one page size which I am getting.
You can issue as many load instructions, but you have to make sure that when processor does out of order, remember out of order comes many ways, right. I will talk about speculative execution in a minute, but if resolution of if let us say take few seconds, let us say 2 clock cycle, then actually you as a attacker hope only 2 instruction would be executed out of order. If you wrote in the if statement you wrote 100 of instruction, by the time it figured out it should not have executed load, it might have executed 1 or 2. So, you can give 200 load here, but processor will not execute. By the time it realized it is not going to execute anymore, and whichever it executed it would try taking actions to clean it up. It will try take action to clean it up. Yes.
Don't go through this memory checking, OS memory checking, because it load from.
Yeah, so load instruction goes through memory checking, but everybody takes time. By the time they realize it, it is already too late.
No, but first it will do checking, then only it will.
Let me think for a moment. I'll get back to that, but basically it still goes to the cache and cache issues the request, and at that point memory checks and data still comes to the cache.
If it is cache is not virtually addressed, if it is physically addressed, then it can do that, because checking will be done later.
I see, okay. So, just to clarify that comment, so there are 2 ways of cache, I did not introduce virtually addressed cache and physically addressed cache. So, if the mapping of virtual to physical you do before cache access, then that cache this data will arrive, but in a virtual address cache this problem will not happen, but that is not in L1, but in L2 would be still physically accessed cache, we still have the same problem. Wherever you have a physically accessed you will have the same problem. So, this is the covert channel, data comes in and nobody took responsibility to clean it. Now, one last idea I want to introduce, because each attack is based on one microarchitectural feature. I introduced out of order, that is meltdown, I will come in a moment, and then I am going to talk about speculative execution. So, speculative execution, think of this is your code, there is a branch statement, assumption is branch statement resolution takes time depending on what pipeline it is, it could be 2 cycle, 3 cycle, whatever the thing is 3, 5, 7, whatever cycle is, and then there is a predictor, because if you did not have a predictor, I want to just to tell you the confusion. If this is a fetch unit, it wants to fetch one instruction every clock cycle, but when you fetch something all you have a 32-bit binary, you do not even know what the inside is. So, by looking at a 32-bit binary you have to make a decision whom do I bring. Let us say this is from location, let us just take a 2 to the power number now, it is a location 32, you got a binary 32-bit binary. So, now you have to decide should I bring somebody 32 plus 4 which is 36, 4 bytes for 32-bit binary, or should I bring somebody from a target if this is a branch instruction. So, there are a lot of prediction this one does, the binary bunch of zeros and ones right now I am seeing, is it a jump or is it a branch kind of instruction? If answer is no, then your PC equal to PC plus 4. Remember this is also a prediction. Now, if this is a branch instruction you still have a question, is it a conditional branch or unconditional branch like a jump instruction. If it is an unconditional branch, then PC has to be the target, but I do not know the target, nobody decoded it yet. So, to know the target you have to wait 1 clock cycle. So, whatever it is, even if it is a conditional branch, now you have to know is condition yes or is condition true or is condition false. That is also a condition you have to know, and all of that evaluation takes time. And in the meantime, the way processor tries to improve faster, they kept something called branch predictor. So, basically last time something from this address came in, what happened to it? Last 10 times it came, what happened to it? Did it take, was taken 9 times? So, maybe then I will predict it as taken, and then I will start executing from there. So, prediction is based on history, and this piece of information is also important for my attack, history. Because if I see you for the first time, somebody asks me predict whether this is a great student or not a so great student for PhD, I do not know, and if I make a mistake, nobody will blame me. You cannot blame a branch predictor if this is the first time this branch came or second time, but if the branch came many times. So, there are lot of algorithms for branch prediction, I will not get into it, but I want to say what attacker will do, attacker will mistrain the branch predictor. In your attack program, I will show you how to do that. In your attack program, you mistrain the branch predictor to make a wrong prediction, because you as an attacker, you cannot take a chance, yeah, the attack code is here, and I hope branch predictor will predict this as taken even before this condition got evaluated. Let us say this could be A and B or C or whatever it is, before this condition is evaluated, then you can't assume. So, attacker has to mistrain the branch by sending lot of branches and making sure it basically produces taken when you want it to be taken. If your attack code is here, then you want to say not taken, right? Any question? So, branch predictor helps the fetch unit to fetch one instruction every clock cycle, even before decode, even before condition is evaluated, and it fetches an instruction and executed an instruction that it should not have executed in the first place, and that is the attacker instruction, and it brings the data to the cache in that window of opportunity when nobody is looking. Now, so that brings me to, now that data came to the cache, all the attacks I am going to talk about at the end they make use of. So, attack starts with something, but ends with cache timing attack. So, what I am going to just first show what exactly is cache timing attack based on the ideas I presented so far.
Excuse me, sir.
Yes, please.
Sir, SS time of memory is more than SS time of cache.
Cache, yet memory is lot more. And the theoretically is true, because it is always, current design always goes through cache. You can have a direct path to the memory, because main memory is much larger, much bigger, much far away from the processor.
Sir, why attacker will not attack on memory?
Oh, attacker, there are attacks that attacks on memory also. You can do the same thing. If you can think memory as the cache and hard disk as the memory, same analogy applies. How long does it take? This timing attack would still apply there, but it is just that time, within that time operating system will take care of everything. So, that is too big a window of opportunity, right? Very good question. So, cache timing attack. So, let me recap all that I said in a animation. So, basically normal execution is happening. Now, you have a branch statement, it can go through the correct path or the wrong path, it does not matter whichever is if or else. So, if for any reason it goes through wrong path, and whenever condition is evaluated, you basically squash them, all the instructions get removed from pipeline, and basically those instructions become no operation. Their effect will not be reflected in the memory, their effect will not be reflected in the register. So, state will not change. So, that is squash, but if it is executed correct path you predicted from certain path, and it turns out the condition was right, then they will retire or complete as usual. So, real problem is this one, when it is executing in a path and these instructions happens to be load, these instructions happen to be load instruction. So, then those addresses, if we can control, it could be kernel memory address, it could be somebody else's address, data came to the cache. This is, so it basically changes that. So, the delay I am going to use that is the side channel. Cache timing is a, in addition to the side channel you already knew, like we talked about electromagnetic emanation, we talked about power, we talked about all those stuff. Cache timing, and in fact community these kind of attacks they still call it side channel attack, but they call it microarchitectural side channel attack or timing side channel attack, and all the other ones are called physical side channel attack. Power, electromagnetic emanation, all that, those are physical side channel, these are known as microarchitectural side channel. So sometimes people get confused which one you are talking. Yes, please.
Sir, when the branch predictor chooses a certain, based on the prediction, it chooses the next instruction, and let's say it's a wrong instruction, that is the branch over here. So the complete instruction cycle will be executed, or just a part of the instruction cycle will be executed?
Both. So it depends on what is here and depends on which instruction. Let us say the if path else, let us say else is the correct path, this is the correct path and you mispredicted, right. So let us say you have 4 instructions and this takes 2 clock cycle. So first of all these 2 would be picked up. If this is a add instruction, it would probably complete all the way and wait in the right backstage, will not commit the data. Let us say it's add R1, R2, R3. So it already computed everything, done everything, but it did not write to R1, it is waiting there. But if you think of this instruction, maybe this it is a division instruction, it needed 23 cycles to complete, it probably completed 1 cycle and it is not even completed. So, but it is still in the pipeline, not in the almost finish line. So, depending on, and these guys will never start if this takes 2 cycles. So, even if you are in a wrong path, depending on which instruction is on the top, how long does it take, that depends on how far they are in the story. But attacker is only in the attack I am going to introduce in few seconds, they are only interested in the load, and that would be the first instruction. So, it is not just load, it is also which address, it is all carefully crafted. If do I want to steal your areas or his area or her area, it is all decided. There is a lot more complexity, remember it is dynamic loading, operating system loads in different addresses. So, that is why many people do not do physical address attack, they try to do virtual address attack. So, those I am not going to try to make complicated, let us just simplify it, right. So, all of that boils down to this, accessing from cache takes very little time, accessing from memory takes lot more time, and all of them. So, before I go there, so when you go to your command line in your Linux system, even Windows I am sure there is equivalent, you type /proc/cpu info, it will show you what are the vulnerabilities and which one is protected or the patch has been installed. So, I am going to highlight some of them and I am going to introduce all these attack. Meltdown, it basically says it is vulnerable to meltdown. So, this is Intel processor, and then say Spectre, I am going to introduce Spectre. It has many variant, I am going to talk about only one variant, the first one, the easy one, and the hard one is left as a homework. So, the Spectre is vulnerable, and then there is also but then there are many other attacks known in the community, and it does not affect Intel processor. That is what it means, not affected means we know about this attack, but in this machine that attack will not have a problem. So, and then there is L1TF attack. So, then basically its mitigation is already installed. So, basically mitigation is PT inversion, but virtual machine is still vulnerable. So, you can get all the information on your processor, what are the attacks and whether the vulnerability fix patch is installed. This is for the Intel processor. Similarly, let me show you the for AMD processor. As you will see, AMD processor, many of the things, for example, meltdown, and this one we recently did the attack. So, MDS, that basically utilizes the internal buffers, load buffer, store buffer or the exchange, that AMD when originally before we did that attack, it basically said it is not affected, and the meltdown it is not affected, but Spectre it is affected, and I will talk about mitigation also, and this is also not affected. So, more aggressive the processor is, it is more vulnerable to lot of types of attack. So, before I go any further, What do you think would be the mitigation of any of these attacks, although I did not talk about those attacks yet? Run sequential, run slow, do not get greedy about anything. If you do not have any money, nobody will attack you. More greedy you are, out of order execution, speculative execution, branch prediction, anything you do, dynamic power management, which I am not going to talk about, any architectural change out there to improve power, performance, security, reliability, that is the cause for attack. And one of the powerful mitigation is for security intensive applications, or when you think something going wrong, stop all these features and execute in a normal slow mode, which is like 5 to 10 times slower. That is a normal mitigation, but there are other any questions on this. So, really what you need to type is whether you do CAD, VI, whatever /proc/CPU info. So, now coming back to cache timing attack, this is the crux of the story. You are accessing different locations and the amount of clock cycle it takes to access, some of them is very, very small and others are very large. The one that is small, that basically means that data is in the cache.
But why cache access time is 400, 300?
Right. So, this particular experiment was done separately, and I want just to everybody to understand, we always say cache access 1 cycle, in reality it is not 1 cycle even on a heat, depending on which processor, because in processor cycle it is 1 cycle, but memory cycle is significantly smaller, it is still synchronized whether it is 4x or 2x. So, those numbers are still fine in the processor cycle count, right. So, but if you do not like these zeros, you can ignore the zeros, but the story is still the same. It takes very small time, somebody takes very high time, but by this you still did not do the attack. I want you to understand. So, what did happen? So, attacker process and victim process, think about it, what happened. So, victim process, there could be a very interesting interplay. So, victim process computed something, right, computed something, brought something in. Attacker process, you have to make sure it can get into the operating system or get scheduled immediately after the victim process, because you want to attack a specific person. Your objective is not I went to shoot a pigeon, I will end up shooting a crow, it is okay, I can boast proudly boast my chest and say I did hit a crow, then that is different story. Here objective is I want to attack a specific person, right. It computes something, brings something to cache, immediately attacker process comes in, and again there are techniques how do you make sure you come exactly after a specific thing. And so, attacker process comes in and it tries to read through the data, and whichever data it takes less time, it knows that somebody brought a data here which was kind of taking less time. You still do not know the value of the data. I will show you how to even know the value of the data. All I am trying to for you to understand that you feel comfortable, yes, I kind of see what is going on here, that some data processor, cache and main memory, attacker or whoever did a load, data came in, and next time somebody is trying to load, if the same data you are trying to load that already appeared, it is going to take less time. We normally use this feature, and this can be done through prefetch also. Attacker process may even do a prefetch, and in fact this is not how actually it works. Attacker process comes in, then victim process, then attacker process, and if that does not happen, then this attack will not happen. You come and you kick everybody out, and there are a lot of techniques, flash, reload, this I will show some snippet of them. You come and kick everybody out, make sure there is nobody, then let victim do the computation, and then quickly come back and then figure out. So, at least what you figured out by knowing this, what address attacker is accessing, what address, that you figured out. We still did not figure out the data, which is what we are interested in, what is the key, what is the secret, that is what we are trying to figure out, because just saying I can get into your house, that is not good enough. Did I get to your house and steal some gold or diamond, then it is important, right. Otherwise, what is the point? I committed a crime, but I did not gain anything out of it, right. So, that I will come, but do any of you have a question that if two addresses, think of this address and this address, because access time is different, you know victim was bringing something to that location. Of course, that is useless if victim was bringing that through speculative execution or something which is thrown away later, then it is useless, right. Now, I am going to explain how do I, once I know the address, how do I know what is the data in there, right. So, there are a lot of techniques used. One yes.
In the previous slide, the time taken less is basically it is data is already in cache.
If the data is already in the cache, if it is a hit versus miss,
The other one is all misses.
other one all misses, and that is enabled by this kind of technique, flash and reload, evict and reload. There are many techniques, I am not going to waste time, but attacker process made a legitimate choice to kick everybody out or kick only out the ones it plans to bring. It is all well crafted examples, it is not like some random stuff, right. So, there are a lot of techniques, I just showed some of them, but it is very well controlled. Now, I am going to go through two attacks and actually answer the next question. We know some which data was in the cache, but what we do not know, basically maybe let us talk about little bit, then I will come back later and talk about it. Start after this. Okay, let us pause here. We will start the Spectre and Meltdown after the break. Thank you.